Hello and welcome to another Bio 265 Anatomy and Physiology in a Nutshell video. Today we'll be talking about capillary exchange. This represents a capillary or very small blood vessel, and the line down the middle represents the division between the arterial end of the capillary, the side that's closest to the heart, from the venous end that's further from the heart. These shapes represent cells around the blood vessel that are relying on the blood to supply them with oxygen, nutrients, and take away their waste. Now, in order to move those substances, oxygen, nutrients, waste, there have to be forces acting on them. In the capillary, there are four main forces that drive fluid movement across the blood vessel wall and into or away from the cells. Those pressures are blood pressure, interstitial fluid pressure, blood colloid osmotic pressure, or BCOP, and interstitial colloid osmotic pressure, or ICOP. The first two pressures involve a pressure called hydrostatic pressure. Hydrostatic pressure exists when you have fluid inside of a container. Now suppose I took a bucket and I filled it with water. I then held it up in the air and I drilled a hole in the side of the bucket close to the bottom. Can you envision that there would be a small stream of water shooting out of the hole that's in the side of the bucket? It wouldn't just be trickling down the side. Because of gravity, water wants to be as flat as possible. So all the water higher in the bucket would be pushing down on the water at the bottom, exerting a pressure on it. Water pushes outward on the sides of its container. Again, fluids want to be flat. The blood vessel can be our container. The fluid inside the walls of the vessel wants to get out. The force it's exerting on the walls we call hydrostatic pressure. And this pressure is going to be pushing fluid out of the blood vessel. The pressure pushing fluid out of the blood vessel is especially strong because there's a pump involved, the heart. Using the previous analogy, adding the heart to the system is kind of like sticking a fire hose into the top of the bucket. Now, the water shooting out the hole in the side of the bucket is going to be going much further with a fire hose in the top because there's a pump involved. The combination of fluid inside of a container, the blood vessel, and the pumping force of the heart, when you combine those two, it creates what we call blood pressure. Blood pressure pushes fluid out of the blood vessel. Out around the cells surrounding the vessel, there's also fluid, interstitial fluid. And that's why we call the second hydrostatic pressure interstitial fluid pressure. Assuming this fluid also exerts a force on the walls of its container, you would assume it would be pushing into the blood vessel. And in real life, it would be pushing in, except that the lymph system gets involved and changes things. The lymph system is like a vacuum. It is constantly sucking fluid into the lymph vessels away from the interstitial space. And the lymph suction is actually so strong that it even pulls some fluid from the capillary itself. Consequently, instead of interstitial fluid pressure, or IFP, pushing into the blood vessel, the suction from the lymph turns IFP into a force that sucks fluid out of the blood vessel. Again, it's a vacuum. The final two pressures are osmotic pressures. In other words, nature loves a concentration balance. If there's a container that has fluid in it, and there's a semi-permeable membrane down the middle, and there are twice as many particles on one side as on the other, the fluid will want to go to the side with more particles. The water travels that direction, diluting the particles until the concentration of water to particle is equal on both sides of the membrane. The cliche saying we use in class is, water goes where the party is. Blood colloid osmotic pressure, or BCOP, is the party inside the blood. It's mostly created by the protein albumin. The albumin creates a concentration or party, and fluid wants to follow it. Consequently, BCOP pulls fluid into the vessel. Interstitial colloid osmotic pressure, or ICOP, is the opposite of BCOP. ICOP is created by the substances and protein in the interstitial space that are pulling fluid towards them or out of the blood vessel. Again, BCOP and ICOP are opposites. Let's give these forces some theoretical numbers and see how they interact. We'll have positive numbers represent forces going out of the vessel, and negative numbers represent forces going in. Let's say that blood pressure is 30 at the arterial end. IFP is 3. Remember, it's a positive number, or going out, because the lymph suction is changing what IFP would normally do. BCOP is negative 28, it's going in, and ICOP is 8. On the venous end, the only number that's going to change is blood pressure. There's significant friction as the blood passes through the capillary, and the whole time the blood's getting further away from the pumping of the heart. Consequently, by the time the blood reaches the venous end, it now only has a pressure of 10. So the lymph's still doing its job, the IFP number is the same, and neither ICOP nor BCOP should change. In a healthy individual, proteins don't cross the vessel wall. Let's do some quick math and see whether the in forces or the out forces are winning on each side. Adding together the positive numbers, representing out forces, we get a total of 41. When we compare that with the negative 28, or the in forces, we see there's a difference of positive 13. In other words, the net force moving out of the vessel is stronger. We have a positive number. Now compare that to the force on the venous end. When we add the positive numbers, we get 21. We compare the difference to the negative 28 that is going in, and we see that the result is negative 7. In other words, the forces moving in are going to win on the venous end. Now between the arterial and venous sides, the only thing that's changed is the distance from the heart. But on one, things go out, and on the venous side, they come back in. Do you see how perfect the system is? There's no need for wasting energy or using transporters. The system moves nutrition and oxygen into the cells on the arterial end, and then pulls waste back into the blood vessel at the venous end. Thank you, and good luck with your studies.